Hello, I'm excited to introduce Coderag-Bench, a benchmark framework designed to evaluate how well large language models generate code when supported by canonical documents, such as official documentation, tutorials, and code templates. The paper is from 2 months ago, and it is published by a team from Carnegie Mellon University, University of Washington, and University of Southern California. My name is Amin Aujahan, and I'm presented today the paper. Coderag-Bench systematically tests retrieval-augmented code generation, where models are given access to external authoritative resources rather than relying only on their internal knowledge. This approach helps improve the accuracy and quality of the generated code. In summary, Coderag-Bench serves as a comprehensive testing ground to assess how these external documents enhance the code generation capabilities of LLMs. The benchmark features 8 coding tasks categorized into basic programming, open domain problems, repository level tasks, and code retrieval. These tasks are designed to test how well a language model can generate accurate and functional code across different scenarios. The purpose of this task is to challenge the models with varying levels of complexity, allowing the benchmark to assess their ability to tackle different type of coding challenge. Five document sources are used to retrieval: programming solutions, online tutorials, library documentation, Stack Overflow posts, and GitHub repositories. The purpose of these sources is to provide external context that the language models can use to enhance their internal knowledge. The benchmark evaluates how effectively the models can retrieve and use these documents to improve their code generation. The solution also has RAG components. We have a data store where it stores documents from various sources, serving as the knowledge base for code generation. Retriever, where it searches the data store. It searches the data store to find the most relevant documents, crucial for providing context to the language model. And of course, a language model that uses retrieved documents and internal knowledge to generate code, with the benchmark evaluating how well this context improves code accuracy. In Coderag-Bench, the generated code is evaluated against canonical documents, known as the gold standard, and tested through execution-based method to ensure functionality. The benchmark assesses how well the entire RAG process, from document retrieval to code generation, enhances the model's ability to generate accurate and functional code across various tasks. The benchmark's strength lies in its structured evaluation process, which systematically tests and measures performance using metrics like NDCG, precision, recall, and pass-K. This allows for rigorous comparison of different RAG systems, making Coderag-Bench a comprehensive test bed. This slide outlines the different data sets used in the benchmarking process. Each dataset serves a unique purpose in evaluating the code generation capabilities of language models. Human Eval and MBPP test the ability of models to generate accurate and functional Python code based on natural language descriptions. Coderag-Bench challenges models with problems requiring incremental code generation, simulating evolving requirements. DS1000 and ODEX focus on more complex open domain tasks involving a variety of Python libraries. Repo-Eval and SWE-Bench Lite involve editing or completing functions in a GitHub repository, representing real-world coding challenges. CodeSageNetPy is used to assess the retrieval of correct Python functions from a large pool of GitHub repositories. Each of these datasets represents a canonical source that helps evaluate how well the models can generate and refine code when provided with relevant external context. From this slide, we compare how different retrieval methods perform across various datasets in the Coderag-Bench framework, highlighting each model's strengths and weaknesses in specific retrieval tasks. In conclusion, best performers were Voyage Code and OpenAI 03, both with embeddings dimension of 1536, show strong performance across all tasks, particularly excelling in problem solutions. SFR Mistral stands out in more complex retrieval tasks, especially when dealing with in repository files. The challenges we got, it's library document retrieval and complex repository tasks are more challenging, with lower NDCG at 10 scores across all methods, indicating room for improvement in these areas. This slide presents the efficiency analysis for document retrieval across various methods, focusing on 4 key metrics. Encoding latency, the time required to encode documents offline. Search latency, the time needed to encode queries, documents, and calculate their similarities. Model storage requirements, the storage space necessary for the retrieval model. Index storage requirements, the space needed to store the index used for retrieval. The table highlights the trade-offs between computational resources, such as latency and storage, and the complexity of the retrieval models. It's important to note that while this table provides valuable insights into efficiency, it does not offer information on the retrieval accuracy or effectiveness of these models, which are crucial for fully understanding the trade-offs. This slide compares the performance of various language models across different code generation tasks, both with and without canonical documents. The scores before the slash represent performance without retrieval, while those after the slash show improvement when using canonical context. In conclusion, canonical context enhance performance by incorporating external context such as canonical documents, significantly boosts code generation performance, particularly in basic programming tasks. Challenge in open domain and repo level tasks. While these are improvement, these tasks remain challenging, especially in more complex scenario like SWE-Bench Lite. Retrieval-augmented code generation shows promise in helping models improve, but there is still a need to enhance how models consume and integrate this into external context, especially in more complex tasks. This slide presents the performance of 3 language models: StarCoder 2 7B, DeepSeek Coder 7B Instruct, and GPT 3.5 Turbo, when using retrieval-augmented code generation across different dataset types. These datasets include general, such as human eval, MBPP, LCB, open domain like DS1000 and ODEX, and repo level tasks, including repo eval and SWE bench light. The table also shows the impact of various retrieval methods, such as BM25, GSlarge, Voyage, and OpenAI re-rank on model performance. The best RAG results for each dataset are highlighted in bold. As key takeaway, this comparison allows us to see how well each model performs in different contexts and with different retrieval methods, highlighting the potential and limitations of each combination in code generation tasks. This slide compares the retrieval-augmented code generation performance of two models, StarCoder and StarCoder 2 and DeepSeek Coder, across different numbers of augmented documents. For basic programming problems using the human eval dataset, the best pass one score with the DeepSeek Coder model is achieved with 5 documents. In open domain problems with the ODEX dataset, the optimal number is between 5 to 8 documents, against favoring the DeepSeek Coder model. For repository level problems using the repo eval dataset, augmenting with 8 documents gives the best performance for the StarCoder 2 model. As a key insight, the optimal number of documents to retrieve varies by task type and model, emphasizing the need for carefully tuning of the number of documents used in RAG to achieve the best results. As a question, can retrieval augmented code generation benefit weaker models? RAG can improve the performance of weaker models, particularly when the retrieval source closely matches the task. The effectiveness depends on the source, with local repositories being more beneficial than open source context. Different tasks benefit from different retrieval strategies. General programming tasks can use various sources, while open domain and the repository level tasks need more targeted approaches to see significant gains. There is still much room to improve RAG systems, especially in integrating multiple retrieval sources effectively and handling complex context-dependent tasks. Can RAG benefit stronger models? RAG significantly improves performance for stronger models like GPT-4 and Claude 3 Sonnet across all sources. Weaker models like Claude 3 Haiku and Gemini 1.5 Flash benefit primarily when using multiple sources, but show mixed results with individual sources. Open domain ODEX, most models struggle to level additional context in the ODEX task, often producing overcomplicated and incorrect code. This highlights the need for improved RAG methods in such scenario. GPT-4o performs well on repo eval tasks, while Claude models and Gemini 1.5 Flash often produce explanations instead of code. The stronger Gemini 1.5 Pro variant shows notable improvement in repository level code completion. Exploring optimal chunking strategies. When multiple documents are added to a model's input, it can exceed context limits. This may impair the effectiveness of retrieval augmented code generation. We explored some chunking strategies. After retrieving documents, only the first n tokens from each document are sent to the LLM. The study finds that most sources are best represented by the first 800 tokens, with Stack Overflow performing best with just the first 200 tokens. For post-retrieval chunking with re-ranking, so in this approach, the model uses re-ranker, BGE re-ranker base to select the most relevant n token chunk from each document. However, within the optimal range of 200 to 800 tokens, re-ranking actually degrades performance. This highlights the limitations of current re-ranking techniques. Peer retrieval chunking. This method involves chunking the documents before retrieval, and only the relevant n token pieces are retrieved directly. The goal is to streamline the retrieval process and ensure that only the most pertinent chunks are considered by the model. The Coderag-Bench is a benchmark for retrieval-augmented code generation, covering various coding tasks with different retrieval sources. The findings with external document retrieval boost code generation, but faces challenging in consistently finding helpful documents. In future, Coderag-Bench aims to support future research in improving RAG systems. Thank you for listening.